Welcome children. Today we are going to take chapter 1 Number System part 8. Representing real numbers on the number line. Visualize 4.26 bar on the number line up to 4 decimal places. 4.26 bar means what? It means 26 is repeating indefinitely. But here we are only going to take 26 up to 4 decimal places. Then we will arrive at this type of number 4.2626, and we are going to expand it step by step. In the first step, we will expand the number line between 4 and 5 up to 1 decimal place, which is very much elementary. What will be the first number between 4 and 5 up to first decimal place? It will be 4.1, and then 4.2, the next 4.3, and so on. Now the question arises, which two numbers will be selected to be expanded further up to 2 decimal places? As you are visualizing, I have selected 4.2 and 4.3. Why? Then move to the question. The first decimal place is 4.2 and the second one is 4.26. So we are selecting the first decimal place 4.2 and the immediate next decimal place 4.3. And we are expanding the number line between 4.2 and 4.3 up to 2 decimal places. Then what will be the numbers in between 4.2 and 4.3? They will be 4.21, 4.22, 4.23, and so on. Now, the question arises, in the next step, which two numbers will be selected to be expanded? Have you any guesses? Yes, they are 4.26 and 4.27. Why? Move to the question. You can see the second decimal place is 6. That is, it is going to be 4.26, which you are already seeing on the number line. And the immediate next one is 4.27. Our number line will be expanded between 4.26 and 4.27. But this time, it will be expanded up to how many decimal places? It will be expanded up to 3 decimal places. Let us see how. Now we are seeing here 4.26 and 4.27 on the number line, and in between you are seeing the numbers which are up to 3 decimal places. The first one is 4.261 and the next one is 4.262 and then 4.263 and so on. The last one you can see 4.269. Usually the last numbers are 9 and then you arrive at the original number. So it's okay. Now let's move to the important part. The two numbers which are going to be expanded on the number line will be 4.262. Why? Because you move to the question, then the number required is 4.2626. So we have already arrived at the 3 decimal places 4.262, which you can easily visualize on the number line. Then the immediate next one is 4.263. Take them on the number line and expand the number line in between these two numbers, but this time up to 4 decimal places. The first one will be 4.2621. The next one 4.62622, and the next one 4.2623, and so on. Do you think we arrived at our answer? The number which is required is 4.2626, which is already on the number line. And circle this number. This is the required number which determines the number 4.26 bar on the number line. So we have represented 4.26 bar on the number line up to 4 decimal places. Visualize 3.765 on the number line using successive magnification. Now let us first understand whether 3.765 is a rational number or an irrational number. Any guesses? Yes, it is a rational number. How did you come to the result? Because it is terminating non-recurring decimal expansion. Well, now let us move to the main part. We are going to visualize this number on the number line. So let us take the first two numbers which are required to be expanded. The first number will be 3 and the next immediate number will be 4. These are the natural numbers or the whole numbers in between which the decimal expansion is going to be carried out. As you can visualize here, just after 3 is 3.1 and then 3.2, then 3.3 and so on up to 4. This decimal expansion is a decimal expansion up to first decimal place. Now we are going to take 3 decimal places. So there are 3 steps in this solution. Here comes the next step. We are going to expand the number line between 3.7 and 3.8 up to 2 decimal places. The first number that comes will be 3.71, the next one 3.72, and the next one 3.73, and so on. Again, the question arises, which two numbers will be selected to be expanded in the next step on the number line? Here we have selected the numbers 3.76 and 3.77. Why? Move to the question. What is the second number in the decimal expansion 3.76? It is 3.76. It is 6. So we have stopped here at 6 and started expanding from 3.76, and the next immediate number is 3.77. Now on this number line you can see the numbers expanded up to 3 decimal places in between 3.76 and 3.77. You can easily visualize that we have arrived at our number which is required. How? First number was 3.761, the second 3.762, and so on. In between, we arrived at our number 3.765 and we have to encircle it. So this is our required solution. Operations on real numbers. Rule 1. The sum or difference of a rational number and an irrational number is irrational. For example, if root 3 is an non-terminating, non-recurring decimal expansion, it means which type of number is it? Any guesses? It is an irrational number. Then 2 plus root 3 and 2 minus root 3 are also irrational numbers. Here you can see that 2 is a rational number. Why is it a rational number? As we have already discussed previously, that all whole numbers come under the category of rational numbers. Root 3 is an irrational number, and the operation over here is sum, addition. And in the next example, 2 minus root 3, the operation carried out is difference, which is subtraction. Hence, the solution of 2 plus root 3 and 2 minus root 3 are irrational. This is a rule. Now check whether 7 root 5, 7 upon root 5 are irrational numbers or not. As we all know, root 5 is equal to 2.236 and so on. It means it is an irrational number. Why? Because it is non-terminating as well as non-recurring. It means the numbers are not repeating. As you can see, 2, 3, 6, none of the numbers is repeating. And in further, you will find that no other numbers will be repeating. So, when we know the value of root 5, what will be the value of 7 root 5? Multiply the value of root 5, which is 2.236, and so on, with 7. On multiplying this value with 7, we will get a number something like this, 15.652 and so on. As you can see that it is non-terminating and non-recurring decimal expansion. Therefore, it is an irrational number. Let us take another example where we have taken a rational number and an irrational number, and the operation carried out between them is division. The first step is to rationalize the denominator. How do we rationalize a denominator? For that, we have to multiply the denominator with the same number and even the numerator with the same number. It means on multiplying root 5 with root 5 both in numerator and denominator, that then will get a denominator which will be a rational number. Why? Because root into root, both the roots will get cancelled and you will get a rational number. Root 5 into root 5 is 5. We need not worry about the irrational number seen in the numerator. We are not rationalizing the numerator, we are rationalizing the denominator. So this is the process, that you are rationalizing a denominator, not thinking about numerator. Now here you can find that our motto was to rationalize the denominator, which we arrived. Now what about the numerator? In the numerator you are having 7 root 5. This result is already there in the previous question. Now that is 15.652. You divide this irrational number with 5, then you will get a number like this, 3.1304 and so on. Can you visualize that this is an irrational number? Yes. So what result do we arrive at?
Equals 3.1304. And so on. It is an irrational number.
Hence we arrive at a rule 2. What is the rule 2? Can you guess? The product of a rational and irrational number is? Just guess it. And what about the quotient of a rational and irrational number? When quotient means what quotient you get when you divide 7 by root 5. Guess. After your guesses, we will arrive at rule 2. The product or quotient of a non-zero rational number with an irrational number is irrational. As you can see, the product also we got irrational, and when we divided it, we got an irrational number, but for that we had to rationalize the denominator. This process is to be carried out, which might be a new one for you. This is called rationalizing the denominator. So understand this process properly. Add and check whether it is a rational or irrational. 2 root 2 plus 5 root 3 and root 2 minus 3 root 3. This is our example, and we are going to check whether it is rational or irrational. Solution. As it is already demanded in the question that you are going to add it, so add it. You can see we have to put the parentheses on both the sides to differentiate this number from the second number. What have we done in this step? Can you realize? We have grouped them. We have used the associative property and done the grouping. Like we have grouped the same numbers in one parenthesis and the other numbers in the other parenthesis where we can see common numbers. Which are the common numbers? Root 2. So we have made a group of numbers which are having root 2, and we have made the second group which are having root 3. What is our ultimate aim? The ultimate aim will be to take root 2 common from this group and to take root 3 common from this group. Here you can see that we have taken root 2 outside the parenthesis. What remains in the parenthesis? Parenthesis means bracket. So 2 remains from the first term, and here you cannot see any number. When you don't see any number, it means what it is? It is 1, not 0, children. Sometimes you confuse that nothing is that means it's 0. No. Because, let me explain you, if it was 0, then 0 into root 2 would have been 0. But here you cannot see 0. What you are seeing over here? Root 2. So what is hidden? Which number is hidden? Root 2 ones are. Root 2 into 1 is root 2. Mind well, let me remind, root 2 into 1 is root 2. Not root 2 into 0 is not root 2. Root 2 into 0 will be 0. So what it is over here, hidden number is 1. Root 2 into 1 is root 2. So which number we have to take from this term? 1. Once again, from this First term we took 2, and from the second term we are taking 1. What will be outside the parenthesis? It will be root 2. Now let us understand the second group, and which number is taken common. Root 3 is taken common because you can see it in both the terms. What will remain inside the bracket? 5. And from this term, what will remain? Minus 3. Now, I need not guess. You are supposed to guess what will be the result. Before I bring the result for you, just you calculate the result fast. Yes, it is 3 root 3 plus 2 root 3. Is it a rational or an irrational number? Make guesses fast. Yes, it is an irrational number. Why? Because here you can see root 2 is an irrational number, root 3 is an irrational number. We already had given a rule. In rule 1, we saw that adding a rational and an irrational number will be an irrational number. Here, the product of rational and irrational is irrational. Here, the product of rational and irrational is irrational. Adding an irrational number, which will be the result of this one, and another irrational number, which will be the result of this one. So, adding irrational plus irrational is irrational. If you don't understand too much, you can understand if this type of numbers root 2 and root 3 are there, then the result will be irrational number. Multiply 6 root 5 by 2 root 5. Let us see what will be the result. On multiplying these two numbers, first we are taking the whole numbers or the natural numbers in the beginning, and the roots will be taken in the next part. So we are making a group of the roots and a group of the whole numbers. So 6 twos are 12. We arrive at the result very easily. And when we have grouped these roots together, root 5 into root 5 is very easy. It is 5. The roots get cancelled. Root 5 into root 5 is root 5 squared, which is 5. 12 5s are 60. Now, here the result is interesting. Why? You can see in the question there are irrational numbers, but your result is a rational number. See, you see that 6 root 5 is an irrational number, 2 root 5 is an irrational number, but on multiplying these two irrational numbers, you got a result which was rational. So these are exceptional cases where you can see that on multiplying an irrational number with an irrational number, you can even get a rational number. Why we came at this result? Because of this 2 root 5. This had made the difference. These two root 5s are making the difference.
Equals 12 multiplied by 5 equals 60. Divide 8 root 15 by 2 root 3.
Let us talk of the next question. Divide 8 root 15 by 2 root 3. 8 root 15 divided by 2 root 3. Now what we have done over here? Here we have distributed root 15 into two numbers, root 5 to root 3. Once again, what is root 15? It is root 5 into root 3. So root 5 into root 3 is root 15. Now why did we do it? So we have to think even further that we can cancel root 3 and root 3 if we do this. There is a possibility that we can cancel root 3 with an root 3 if we bifurcate root 15 into two numbers, root 5 and root 3. This is called the simplified form of root 15. Well, so we eliminate root 3 and root 3 both in numerator and denominator, as well as we can simplify 2 and 8 because 8 comes in the table of 2. 2 fours are 8. So what remains in the numerator? 1 4 is remaining and 1 root 5 is remaining. These two root 3's are getting cancelled. They are getting eliminated. Once again, root 3 is getting eliminated. 2 fours are 8. So 4 is over here and 1 root 5 has remained. So it is also over here. Now you can see that on dividing an irrational number with an irrational number, we got an irrational number. Hence we conclude a rule. Rule 3. If we add, subtract, multiply or divide two irrational numbers, the result may be rational or irrational. Why rational? See over here. The result is rational. So it can be rational or irrational. Now let me just ask you a question. Could this have been a rational number? Yes, if this root 5 was not there, then it could have been a rational number, right? That's why they are saying that the result can be rational number or an irrational number. There are two options open in these cases. Which case? When we add, subtract, multiply or divide two irrational numbers. We are talking of two irrational numbers, not one rational and one irrational. The rule 3 talks of two irrational numbers. Rule 1 and rule 2 was talking of one rational and one irrational number. Once again, rule 1 and rule 2, we saw examples about one rational and one irrational number. In rule 3, we have taken examples which are having both irrational numbers. Exercise. We are going to check whether root 2 plus 21 and pi minus 2 are irrational numbers or not. As we all know, root 2 is equal to 1.4142 and so on. So on adding 21, which is a whole number or a rational number, you can call it rational number because natural numbers, whole numbers, all are rational numbers. So 21 comes under the same category of whole numbers, natural numbers and rational numbers. Whichever name you want to give, you can give. But ultimately it is a rational number. Now on adding a rational number with an irrational number, what does the rule say? Is always an irrational number. So 21 plus 1.4142 will be 21 plus 122 point these numbers and so on. As we all know, the value of pi is equal to 3.1415, so on. We are going to subtract 2 from it. Any guesses? What will be the result? Yes, 3 minus 2 will be 1 and after a point the same number will be repeated as in the question, as in pi. Hence it is an irrational number. Why? Because it is non-terminating and non-recurring. Decimal expansion. Classify the following numbers as rational or irrational. 2 minus root 5. As we all know, root 5 is equal to 2.236 and so on. We also know that it is an irrational number. Why? Because it is non-terminating, non-recurring decimal expansion. 2 minus root 5 is equal to 2 minus 2.236 and so on. 2 minus 2 will be 0 and the other numbers after the decimal point will be as it is. As you can see, they are non-terminating and non-recurring. Are they so? Yes. Then what type of number will it be? It is non-terminating and non-recurring decimal expansion. Hence, what type of number is it? Is it a rational or an irrational? Well, right, it is an irrational number. In the next example, you are seeing that 3 plus root 23 minus root 23. Now, in the first step, we'll take this root 23 outside the bracket. So what will happen? Any guesses? Yes, both these root 23 will get eliminated. Here they are. Plus root 23 and minus root 23 is getting eliminated. So what is remaining? 3. 3 is, can you represent 3 in the form P upon Q? Yes. You can represent all whole numbers in the form P upon Q. How? Just divide them by 1 and the form changes. It will be a P upon Q form. And whenever you can represent a number in P upon Q form, it is called a rational number. It is of the form P upon Q, hence it is a rational number. Now here you can see the example 2 upon 7. It is multiplied by root 7 both in numerator and denominator. Now we are going to find out whether it is a rational or irrational number. Any guesses what are we going to do? Yes, we will remove root 7 both in numerator and denominator. On eliminating this 2, root 7 will be remaining with only 2 upon 7. And what type of form is 2 upon 7? And if it is of that form, then what will be it? What will be the number? It will be a rational or an irrational number. So let us first find the first step that we are going to do. In the first step, we are going to eliminate root 7, both in numerator and denominator. So we got 2 upon 7. And I even asked what type of form is it. So here it is of the form P upon Q. I even asked that if that is the form, then what type of number will it be? So if it is of the form P upon Q, the number is a rational number. Here is the next example, 1 upon root 2. We have to find whether it is a rational or an irrational number. I have once explained you that we have to rationalize the denominator first. The first step is to rationalize the denominator. How did we do it previously? Just recall, we multiplied by root 2 mean both in numerator and denominator. It means we multiply by the same number both in numerator and denominator. Here it is. We are multiplying by root 2 both in numerator and denominator. So what is the purpose of doing it? The purpose is to rationalize the denominator. On rationalizing the denominator, we get 2, which is a rational number. Hence the name came that rationalize the denominator. I also told you previously, you need not worry about the numerator. In numerator, you might get an irrational number or a rational number. That is not the question. The first step is to rationalize the denominator. Once the denominator is rationalized, just multiply the numbers in the numerator. They are here it is root 2 upon 2. We know the value of root 2, and then dividing it by 2, we get this number 0.7071 and so on, as it is quite evident that it is a non-terminating and non-recurring decimal expansion. Hence, what type of number is it? Yes, it is an irrational number. Simplify the following expressions. Here is the first example for you. You have to simplify it. Here we have applied the rule root a plus root b into root c plus root d is root ac. How did we come at the result root ac? From here we took root a and from here root c. Then the same root a is multiplied by root d. In the third step, you multiply root b by root c, and in the fourth step, again you multiply root b by root d. This is the rule. The same process we carried out. First we multiplied 5 by 2, so we got 10. Then we multiplied 5 by root 5, we got 5 root 5. Now we have completed the process of 5. Now we'll do the process of root 7. For root 7, we multiply root 7 by 2, we get 2 root 7. Here I want to explain you that you cannot write root 7 in the front and 2 in the back. You have to put 2 before root 7. Like this is the mathematical expression. How to express this number, that is 2 root 7. You cannot write this 2 behind. So be careful about it. Be systematic in your writing. So okay, let us move to the point that root 7 into 2 is 2 root 7 and root 7 into root 5 is 7 5s are 35. Therefore, root 35. This is your result. Here is the next example. Here the same rule, but here the rule is a different identity. It is a minus b and a plus b. But since it is root, so we can say it is root a minus root b and root a plus root b. What is root a minus root b and root a plus root b? Okay, let me explain you one identity which we have previously done in previous classes, that was a minus b into a plus b, and that is a squared minus b squared. So here also the same process is applicable. Root a whole squared will be a and root b whole squared will be b. It means root b into root b is b and root a into root a is a. Right? Because it is root a whole squared minus root b whole squared, which will be a minus b. Here is your solution. Root a whole squared. So root 11 whole squared and root b whole squared means root 7 whole squared. A squared minus b squared. This identity is of a minus b, a plus b. We have already studied about it in 8th class. Once again, I am repeating the identity. A minus b into a plus b is a squared minus b squared. So we'll get root 11 squared is 11 and root of 7 squared is 7. I already explained you when the same roots are multiplied, the root gets eliminated and only the number remains. So 11 minus 7 is 4. And the next example, this is a plus b whole squared. A squared plus 2ab plus b squared. You can even say that a squared plus b squared plus 2ab. So here it is root a squared, therefore it will be a, root b squared, and this will be b, and 2ab means 2 into root ab. So here how the process is: root 3 squared. It means root a squared. It is 3. Root b squared, 7 plus 2ab. A squared plus b squared plus 2ab. The calculation is over here. I need not repeat it. Here you are having a case where you can even add 3 plus 7. In the previous cases, there was nothing that you could add. But here you can add this 3 and 7, you get 10. So you should add them. But you cannot add this 2 with it. Mind well. This 2 is a separate term. It is attached with root 21. Don't commit the mistake of adding this 2 also. It should remain separate. 2 root 21 need not be added with 10. Some students commit the mistake that they add these two numbers as well as 2 and they come at the result 12, which is wrong. Just add only whole numbers. You can even say this is a corrupted number. You cannot add with this whole number. Right? Something that type of idea you keep it in your mind. This is a rational number. We are adding the two rational numbers and we are not adding this irrational number. Recall pi is defined as the ratio of the circumferences say c of a circle to its diameter say d. Then pi is equal to c upon d. This seems to contradict the fact that pi is irrational. How will you resolve this contradiction? Now when we measure with the scale, we obtain only approximate values. You already know that in scale we do not get exact value. Now this is something related with science. It is called effect of polarization. Just you visit some sites and understand what is polarization effect. Because of that you do not get accurate values, you get only approximate values. Another thing is also that what is a point? Inside a point also there are millions of points which are invisible to us. So when we say 0.5, there is again so many numbers, so many smaller points in this 0.5, which we already even saw in this previous cases on number line. So again we can say that whatever values we are obtaining are always approximate values. We do not get exact values. So if we are having approximate values, then either circumference or diameter is irrational, or both can be rational numbers. Means if you say it's some number like zero point 0.2 on number line, then it is not 0.2, it is 0.21357 and so on and so on. So the value of circumference can be such irrational number or diameter can be irrational number. For example, if I say it is 3 upon 5, then this is not, circumference is not 3. It is the approximate value. Then what is its exact value? It can be an irrational number. 3.1125737.37 and so on. Suppose I say the value of b is 2, then it is not 2. It is can be an irrational number 2.37428 and so on. Now here also I took an irrational number, here also I took an irrational number. So either circumference was irrational or the diameter was irrational. Why? Because 3 and 2 were approximate values, not exact values. It's not possible also to find exact values because within a point there are innumerable points. Little bit you can go to spiritual part. कण कण में भगवान ऐसा माना जाता है. So what means that? In within each कण there are so many smaller points, or both can be irrational numbers. Further, phi can be approximately represented as quotient of two rational numbers, that is 22 upon 7 which is equal to 3.142857 and so on. This value you are very much familiar with. This is the value of pi and it is an irrational number. So whenever we write the value 22 upon 7, we are again arriving at an irrational number. This number you are familiar with. Usually in previous classes you are familiar with only 3.14, but now you are learning what is this 3.14. It is an irrational number. Rationalize the denominators of the following. 1 upon root 7. Here you can see that root 7 is an irrational number. We have to convert it into a rational number. How can we do it? As I told you previously, to convert any irrational number in the form of root, we have to multiply by the same irrational number, which is also of the form root. So, root 7 will be multiplied by root 7 to convert it into a rational number. Now, how does it work? Let us see. Here you can see that root 7 into root 7 is equal to 7. It means the roots have got eliminated. But during this process, we have even multiplied by root 7 in the numerator. Why have we done so? As you have learnt in the lower classes that to convert a fraction into an equivalent fraction, we multiply its numerator and denominator by the same number. The same process we carried out over here. We multiplied the numerator and denominator by root 7. That's why we are getting root 7 in the numerator and in the denominator we got 7. It means we have rationalized the denominator. 7 is a rational number. Now mind well, here we are concerned with rationalizing the denominator only. We are not concerned with rationalizing the numerator. The numerator can be an irrational number. So don't mistake that why you got root 7 over here, it means you have done something wrong. No, it's totally correct. The numerator can be a rational number, but the denominator has to be a rational number. Here you can see 1 upon root 7 minus root 6. We have to convert this denominator into rational number. Which identity will be the best suited over here? So let us just guess. Root 7 is to be converted into rational number. For that we will multiply root 7 into root 7. It means it will be a square. Here root 6 will be multiplied by root 6. It means it will be b square. A squared minus b square. Which identity works over here? A plus b, a minus b is equal to a squared minus b squared. We are already having a minus b. We will require a plus b. So which number will we require? Let us see in the next step. Here it is a minus b root 7 minus root 6 and a plus b is root 7 plus root 6. As I previously told you, if we multiply by a number in the denominator, we need to multiply by the same number in the numerator. So multiplying the numerator and denominator by root 7 plus root 6. As I already explained you, a minus b into a plus b is equal to which identity? Is equal to a squared minus b squared. So ultimately the roots will get eliminated in the denominator. Let's see how it works. Yes, you can see over here root 7 into root 7 a squared is 7 and root 6 into root 6 b squared is 6. And the identity is a minus b into a plus b. The denominator got converted into a rational number. 7 minus 6 is equal to 1. What about the numerator? In the numerator, we are having 1 into root 7 plus root 6 is root 7 plus root 6. I already mentioned you, we are concerned with rationalizing the denominator. You need not worry about the numerator. The numerator can have an irrational number. So the solution is root 7 plus root 6. Here is the third example. Root 7 minus 2. We have to convert this into a rational denominator. How will we do it? Can you guess? Yes, again the same process is working. Root 7 plus root 7 plus 2. Because here it's a minus b and we have multiplied with a plus b. Root 7 plus 2 both in numerator and denominator. So ultimately we got a squared, that is root 7 squared, that is 7, and b squared, that is 2 squared, which will be 4. 7 minus 4 is 3. In the numerator, we are remained with root 7 plus 2. Once again, recall which identity has worked over here. A minus b into a plus b is equal to a squared, root 7 squared, and minus b squared, that is 2 squared, that is 4. Laws of exponents for real numbers. Let us recapitulate whatever we studied in class 7. A raised to m multiplied by a raised to n is equal to a raised to m plus n. A raised to m whole raised to n is equal to a raised to mn. A raised to m divided by a raised to n is equal to a raised to m minus n. So in the product, we have the powers added, and when we take the division, we have the powers subtracted. And here m is greater than n because we are talking of natural numbers. If m was less than n, then we would not get a natural number, we'll get an integer. And the final law is a raised to m multiplied by b raised to m is equal to ab raised to n. Here the bases are different, but the powers are same. So we'll have a common power and we'll multiply the bases. So these are the laws for natural numbers. Let's talk about the extended laws for real numbers. Here a is greater than 0, be a real number. It means the base is a real number. And m and n are rational numbers. Then the same laws will be applicable over here also. A power 0 is equal to 1. This is also a law which is applicable for real numbers. But we cannot say over here because we are having m and n natural numbers, so we did not use it over here. Now this one is a new law for you. It is not over here. Why? Because minus m is not a natural number. Now a upon a raised to m is equal to a raised to minus m. Learn this new law. This is a new law which is for real numbers. And we are going to do sums based on this law. And this is one crucial law which is particularly applicable over real numbers is about root. How do you get a root? A raised to m upon n. Now the denominator n will remain outside and inside the root you get a raised to m. Once again, the denominator will move outside the root and within the root you will get a power m, a raised to m. Understand this law properly. These two laws are new laws which are applicable over here and you will have to do sums based on these two laws also. Examples based on laws of exponents on real numbers. Find 125 raised to 1/3. Now, how can we write 125 in its simplest form? 125 is the multiplication of 5 times 5 times 5. This is also called prime factorization. We can say that these are prime factorization of 125. So first find the prime factorization of 125. This is the simplest form in which you can write. The power is as it is raised to 1/3. Now can you guess how can we write this 5 times 5 times 5 in a power form, in an exponent form? Guess, please guess. Yes, you are right. It is 5 cubed. 5 cubed into 1/3. 1/3 was already there in the power. The base is 5. 3 and 3 will get eliminated in numerator and denominator. We will be remained with 1. 5 power 1 is 5. Now here's the next example, 32 raised to 2/5. First find the prime factorization of 32. Can you guess what will be this prime factorization? We have to do certain prime factorization orally when they are simple. It is a simple prime factorization. Yes, 2 into 2 into 2 into 2 into 2 means 2 will be taken 5 times. Here you can see we have taken 2 5 times. Raised to 2/5. Now one more guess you have to do. How will we write this 2 5 times in a power form, in an exponent form? Yes, you are correct. It will be 2 raised to 5. 2 raised to 5 into 2 upon 5 is equal to, now here, which law we are using? Can you recall? A power m power n is equal to a power mn. So we are removing this power outside the bracket and it will come outside. So we get 5 into 2 upon 5. Once again, a power m whole power n is equal to a power mn. 5 and 5 will get eliminated in numerator and denominator. We will be remained with 2 in the power. The base is already 2. We are not disturbing the base. The base will always be as it is in the question most of the time after we take the prime factorization. After we take the prime factorization, the base is same. So we are not disturbing the base. We are doing calculation in the powers. So 5 and 5 get eliminated. We are remained with 2 in the power. 2 squared is 4. Let us find 1 upon 3 raised to 3 whole power 7. Now, do you remember that I already told you the one law which will be applicable in the sums that will follow? And I even told you that's a crucial law. Just recall it. Yes, here the law which works will be 1 upon a power m is equal to a raised to minus m. So what will be 1 upon 3 cubed? Guess what will be the result? Yes, it will be 3 raised to minus 3. Now let us see how is it working. Here, see, your guess is correct. 1 upon 3 cubed is equal to 3 raised to minus 3. We have not disturbed 7 over here. It's as it is. Now, after we apply another law, we will disturb this 7 also. Which law will be applicable over here? The second law? Just guess. Yes, the law is a power m whole raised to n is equal to a raised to mn. That is equal to, here you can see 3 raised to minus 3 into 7. So minus 3 into 7 is 21. Therefore, the result is 3 raised to minus 21. How did we get it? We used the law a raised to m whole raised to n is equal to amn. Now this is the second question. 11 raised to half upon 11 raised to 1/4. Here we have to apply a law. Which law can you recall it? Yes, it is a power m upon a power n. So that will be a raised to m minus n. When in division, we subtract the powers. So on subtracting the powers, we will take LCM and then we'll get the result. Let's see how we are taking the LCM of the denominator. Here it is. You are familiar with taking LCM, so I need not explain how to take LCM. And we got the result 11 raised to 1 upon 4. Here is the next question. Again the same 125 is there which we did in previous sum, but here the power is different. It is minus 1 upon 3. Now can you guess what will be 125? It will be 5 raised to, yes, very good, 5 raised to 3. And then you will multiply it with minus 1 upon 3. Let's see how it works. Here 5 cube multiplied by minus 1 upon 3. This cube will move outside the bracket. So you will get 3 into minus 1 by 3. 3 will get eliminated and you will be remained with minus 1. Here the 3 and 3 will get eliminated and you will be remained with minus 1. Mind well, you have to move this 3 outside the parenthesis. You don't do like this. Here you don't eliminate. See, if you are trying to eliminate over here, then you are doing it wrong. This 3 is inside the parenthesis and you cannot eliminate it like that. You have to move it outside the parenthesis. And the final step is also remaining, that after 5 power minus 1, what it is? A raised to minus m is 1 upon a raised to m. It means the minus sign will get eliminated. You will get 1 upon 5 raised to 1, and 5 raised to 1 is 5. So the final answer is 1 upon 5. Here is an assignment for you. This is the repetition of the question which we have already done in the previous slide. So you follow the same method and do this sum.
Simplify the following expressions. Practice the sums from 1 to 5 in your notebook.
Here is an assignment 2 for you. Rationalize the denominators of the following. All these sums are practice sum. We have done this type of sums in the previous slide. If you don't understand, watch the slides and you practice it. You will definitely work it successfully. All the best to you. Even these sums we have practiced in the previous slides. You just refer to the previous slides if you are missing any steps or if you find some confusion. Everything is there in the previous slides. This all assignments you are supposed to do in your classwork.
Thank you.